start it whenever you're.
All right, sounds good. All right, hi everyone. My name is Grace Cummings. I'm a Letterman Fellow here at Fermilab. I wanted to say first and foremost that I'm sorry that I can't be there in person. You might be able to hear, but I'm a little bit under the weather, so unfortunately that has made me have to be taking this a little bit remotely today. But okay, so this morning I'm going to introduce you to the standard model of particle physics, and then after me, Janet will go and explain to you how we study this at the LHC. And you can see from here, I'm on the CMS experiment, so a lot of my examples are going to be coming from CMS, but Janet will introduce you to that a little bit more in a bit. So I wanted to start kind of in the beginning. I'm going to give you a brief overview of the scientific method. I know most people here probably, know what that is, but when you're thinking about how to investigate something scientifically, first you start with an observation or question. Then you want to form some hypothesis. So based on your question, you want to think about okay, well, what could possibly be the answer? What's the reason for this? Then ideally, you formed that hypothesis in a way that you can design an experiment to test it. You design that experiment, you do that experiment, and hopefully from there, you're able to draw some conclusions, which ultimately leads us back into a cycle where you just have new observations and new questions. That's pretty much always how it goes. And that's how it goes with the standard model. So of course, the standard model seeks to address some question, the observation in question that the standard model likes to talk about. And here you'll see this diagram throughout my talk, and I'll introduce it in a little bit, is ultimately what is matter and how does matter interact. This is what fundamentally the standard model is about. It's hoping to have a description of matter and all of its interactions. So that brings me to this. This is the standard model basically in one picture form. Here we have all of the known fundamental particles captured in one complete diagram, and we'll step through this as we go through my talk. And it also shows the interactions between these particles. So it has, again, like I said, all of the known fundamental particles and 3 out of the 4 fundamental forces. This is the first thing you'll be suspicious of. I'll get to that in a little bit in my talk. But for the most part, this describes matter pretty well. So then let's take a few seconds, to walk through this. So here in this first box, oh, excuse me for a second. Muting worked and you didn't hear me have a horrendous cough. So I'm sorry if I don't get that happen, don't get that muted fast enough. But here in this first block, I have all of the matter particles of fermions. So these are all, half integer spin particles. This is really what makes up the stuff of the universe. And here there's, a few more things that are interesting about this. This first column is your everyday matter. So everything that we normally interact with exists in this column of the standard model. You have, your up and down quarks, which form, protons and neutrons. This is what makes up all the atoms that we see in our day-to-day lives, with electrons as well, of course, in the orbitals around the atoms, which are responsible for how they interact with one another. And then you actually have the electron neutrino. People probably don't normally think about interacting with the electron neutrino on a daily basis, but this is responsible for radioactivity. So all the radioactivity that you might see or that you're talked about in day-to-day life, that's coming from this column right here. Now, of course, we have these second 2 columns, and these are all unstable matter. So this is what is accessible at accelerators or colliders. So this is really where, I focus my research, where a lot of the research at Fermilab is focused, is into, this regime over here. Of course, there's also cosmic sources of these types of things, but we can make them in mass at accelerators and colliders. So this is the matter part of the standard model. Then moving over, we have the bosons or the force carriers. So the way that you want to think about these is okay, all the particles on the other half that we just talked about, they have to interact with one another. And the way that those interactions happen is through the exchange of these particles here. And I know that's kind of a weird concept, but I think a really nice analogy that you can think about is when you have 2 basketball players and they're throwing a basketball back and forth. They're communicating with one another, they're exchanging information, but it comes from actually throwing that basketball back and forth. They don't touch each other in this exchange, but they still can do it through the basketball. And you can think of these bosons over here, these 4 different ones, I guess 5 if you consider the plus minus of the W, as that basketball that's being, exchanged back and forth. So the first one is the gluon. So gluons mediate the strong force. This is one of the 4 fundamental forces that we have. Gluons hold together quarks and make bound states. So here I actually have, a very naive drawing of a proton. So here you have your up, and your down quark, and then they're exchanging gluons, which actually hold them together. Gluons interact with anything that carries color charge. So that's all of the quarks. So that's this kind of region of this diagram up here. Quarks and gluons carry color charge, and they're the only particles that interact via the strong force. Next, we have the photon, and this is probably the force that everyone is most accustomed to thinking about. Photons mediate the electromagnetic force. So this is how electrically charged particles interact. This is when you say, that oppositely charged particles attract, same charged particles repel. That is all happening through the exchange of a photon, which is mediating the electromagnetic force. Anything that's charged interacts through the electromagnetic force. That's all of these particles up here in the standard model. And then finally, that brings me to the weak force, where the W and Z bosons are mediators. The weak force is what's responsible for nuclear decay. So here we have our example of beta decay. And the way that you actually have this happen is that you have, a neutron in your atom converts to a proton by releasing an electron in a neutrino. And here, this is a Feynman diagram. I'm not actually going to go into really how you interpret these, but you can see that we have, the up and the down quarks and make up your neutron. They exchange a W boson, and then you actually end up getting your proton at the end. And this is what's happening here. And this is how you can think about interacting with the W and the Z boson in your day-to-day life. We of course can make these directly at colliders, and then that's a part of my study. But this is how they fit into the standard model as force carriers. And then anything that has weak isospin, so weak isospin is this value, can interact with the weak force. And this is then basically everything in the standard model at this point. Each one is getting larger and larger of the things that it can interact with. Finally, that brings us to the Higgs boson. So the Higgs boson is really special. I know that everyone says that, it's kind of trite at this point, but it really truly is. The Higgs boson allows for the unification of the electromagnetic and weak forces. So the photon and the W and Z boson are actually carriers of the same, of a similar force that is then broken down, which I'll talk about a little bit more as we go through my talk. The Higgs boson is also special in that it provides mass to the W and Z bosons and all of the charged fermions overall. So this is really why it kind of brings the entire standard model together. And then, of course, for every matter particle, there's actually an antimatter particle as well. They're fundamentally the same, except they have opposite quantum numbers of all of their standard model particles. And it's easiest to think of that in terms of charge. So for example, an electron that we like to think of, our matter electron is negatively charged. A positron, which is an antimatter electron, is just positively charged. So you can think of it as just the opposite of those quantum numbers. And actually from this was really exciting, this came out a few weeks ago, the ALPHA experiment at CERN actually showed that antimatter interacts with gravity the same way, at least as far as we can see. It also falls down, which was something that no one had actually measured, and now they have, and that's really exciting. So for every one of these particles, there's also the antimatter partner. So with that, I think that this is kind of a natural place to stop for the first time to ask any questions. Here I have a particle identity quiz. Hopefully this QR code still works, where you can picture it and you can answer some questions and discover what type of particle you are. I did it last year and I was a W- boson. I'm not sure how we want to do questions. Since I'm not there, I can't see hands. So if someone wants to ask any questions now, or we can continue on.
Yeah, so there are questions in the chat, which I can't see. Somebody requested going back a couple of slides, but I think that's going to preclude you from actually doing the quiz.
No, I have the thing open. All right, oops.
Okay.
Let's see, two slides. So the Higgs boson.
We do have a question on.
Yeah, there's another question. Go ahead.
Yeah, what is a boson?
What is a boson? So bosons are particles. Excuse me, one moment. I have to mute because I have to cough. Particles that have integer spin. So this is where you can have 0 spin, spin of 1, spin of 2. The Higgs has spin of 0, and the rest of the bosons have spin of 1. But it's really a spin state, and that allows the bosons to interact differently with different particles. So it's easiest to describe what a boson is in comparison to what a fermion is. So you have, think of electrons, and they exist in levels in your atoms, right? They exist in orbitals. And from Pauli's exclusion principle, they can never be in the same state. That's because they're spin 1/2. They have to be separate. Whereas bosons actually don't have that. They can all exist in the same state, which allows them to have slightly different properties. Does that hopefully that kind of answers your question. I don't know, the student who wanted me to go back 2 slides, do you have a question on this slide before I get into
No,
the
they said they got it. Are there any
they
more
got it?
questions from the audience?
So why does the Higgs boson only interact with certain fundamental particles?
That's a good question, and that's something that we're studying. It interacts with most of them. We actually don't really right now know, I was going to say, the interaction with the neutrinos. That's still kind of an open question. But it ultimately comes down to the charges of the particles that they have. Since it's related to the symmetry breaking between the W and Z and the photon, that kind of shows you that it should be, it should be related to all the particles that can also interact with. Is kind of the naive way to see it. And then I also saw that there's a question on the chat of what is the antiparticle of a neutrino, because it has no charge. So charge is not the only quantum number. There are other quantum numbers that these particles have, like the weak isospin is an example. I know that's kind of an esoteric one, but that is a value that these particles have. So you also have the opposite of those. Neutrinos are special in the fact that we actually don't know what type the particle-antiparticle relationship between neutrinos, I think, is still kind of an open question. If they're Majorana neutrinos, they're their own antiparticle. If they're not, then they actually have separate particles. And these are things that we're exploring in science right now. And then there's a question that says, are all these considered quarks? I'm not totally sure exactly what you're referring to, but the quarks in the standard, can you guys see my cursor? I realize I haven't asked. Okay. These are all of the quarks in the standard model right here. So not everything that's circled here is considered a quark, but the up charm top, down strange and bottom are all considered quarks. Do we have more questions in the room?
Anything else, guys? I think we're good here, Grace. Please continue. Oh, we got one more in the chat, but maybe we should take it a little bit later.
Well, it's an easy one. So photons in this diagram are also light. Yes, photons are light kind of all the time, which is an exciting, which I always find exciting. So yes, photons in this diagram are light. All right. So that probably just leads to more questions than answers, but that's one that we can move through. All right. Also, can we split protons? Yes, of course. That's what we do. Well, I guess maybe split is a strong word, but when we collide them, we're actually, at the LHC, we're actually colliding the particles inside. We don't actually collide the protons. But okay, I'm going to take a break. I'm actually going to close the chat. Otherwise, I'll keep answering questions, and we can get into the next part of my talk, which might answer some of these questions. All right, so I started with, what is a scientific method? And I promised that there was a reason that I wanted to start there. Because then that ultimately leads into what is a good scientific model? And a good model, in my mind, must, do 2 things. It must make predictions based on the model itself. It has to be able to allow you to form some sort of hypothesis. It must make some prediction about what will happen in the natural world. That's the first thing it must do. And the second thing it must do is ultimately describe the natural world. So those predictions that it makes, well, they better, actually describe the world that we live in. Otherwise, your model doesn't actually give you any understanding of what's happening. And I hope that makes sense. Ultimately, you need to have your model be able to predict that something would happen, and then that thing actually should happen. And that's kind of shows you that it's good. This is like, things like projectile motion. Like we can model that, and it ends up working. So we know that that's actually giving us some understanding of the world around us. So the standard model definitely describes the natural world. It includes all of the known particles so far and 3 of the 4 fundamental forces. I mean, that's a lot of the world that we live in that this describes, and it does it incredibly well. So it definitely checks, the first box of describe the natural world. The second thing that it does, and this is really what makes me particularly excited about the standard model as, as a thing to study, is that it makes really, really good predictions. So here I have a diagram, and it'll take, let me walk you through it so it makes a little bit more sense. So here along the top, I I have when a particle was predicted. So this is, based on math and based on understanding when a particle was, postulated to exist. So here, you have the neutron predicted, here you have antiparticles proposed, pions, so on and so forth. The Higgs mechanism was, of course, predicted sometime in the 60s. This is when we predicted something would happen. And then along the bottom, I have when something was discovered. So here, we have the neutron predicted right around 1920. Then, of course, you have the neutron discovered a few years later. We had the Higgs predicted in the 60s. We had the Higgs boson discovered in 2012. So over the last 100 years, discovery has followed prediction almost to a T. Now, of course, the muon did not fall into that. And that, of course, has the classic who ordered that from Rabi. But for the most part, the standard model has had an incredible track record with predicting particles before we actually discovered them. And there's a few reasons why this has been the case. It ultimately all comes down to conservation laws. So kind of my favorite example is from beta decay. All right, so we knew that scientists in general, in the early 1900s, they knew that radioactive decay was a thing. And then we had an idea of like the quantized nature of the world. So you have, some excited state. Whenever you have something happen, it then decays into some ground state. And since it's quantized, you would always expect that, excited to ground transition to always emit the same amount of energy. So when you had this beta decay with this electron emitted, they're like, okay, well, this must be an excited state of this atom. The decay leads it to this ground state. So you should just have one sharp peak in energy from this quantized system. Well, of course, they measured it. And that ends up not being true, actually. Your electron does not get emitted with the same amount of energy every time you have a beta decay. And that doesn't seem to make sense in a quantized system and how we understood the universe at the time. You actually get something like this, where it has, a smooth falling spectrum of all of the energies that it can have when it's emitted from this atom. And we would expect it naively to have a single valued peak because of, conservation of energy and our understanding of the quantized nature of the world that we live in. So because of this, Pauli proposed that a small neutral particle must actually be carrying away the excess energy in this interaction. He was like, okay, this transition must be quantized. The electron clearly isn't carrying all of the energy, so something else must be carrying it away. And from that, he proposed, the existence of the neutrino. That electron neutrino must be what's carrying away the rest of this energy. And then, of course, 36 years later, neutrinos were actually detected. So this is how, a fundamental idea of a conservation law, just conservation of energy, directly leads to the postulation that a new particle existed. And conserved quantities, so in this case, energy was the conserved quantity in this interaction, and symmetries go hand in hand. For every conserved quantity in the universe, there's a symmetry of this interaction. And this is a really, really powerful theorem in physics. And it's called Noether's theorem, and it comes from Emmy Noether, who she was the mathematician that originally put this down on paper. And it's really, fundamental to everything that we do in science. And this isn't the only, of course, energy conservation isn't, of course, the only one that you can easily see. Spatial translation is what gives momentum conservation. So this is, symmetry of the interaction. A falling to B should be the same in this area of space as it should be here. There's no reason that the momentum of this movement should be different just because A and B have moved slightly. And this is ultimately, there's a symmetry in this interaction, and this is what leads to momentum conservation. So I just want you to, I know this is kind of, it's kind of a weird thing to think about, but for every symmetry, there's a conservation law. For every conservation law, there's a symmetry. And this is really fundamental to how we understand the standard model. So for each, again, I'm going to say it again because it's really important. For each conserved quantity, there's a symmetry of the interaction. This gives us another handle in order to understand interactions. Things that violate the symmetry are not allowed. And here I have, the three forces or interactions in the standard model and then what they end up doing. So the electromagnetic force, of course, whenever you have an electromagnetic interaction, it has to conserve electric charge. What this ends up doing mathematically is is obeying a U1 symmetry. I'm not expecting you guys to know what this U1 symmetry is, but I want to say like there's, conservation of charge. We obey this U1 symmetry. For the strong interaction, I said that everything that interacts via the strong interaction has something called a color charge. Bound states must be colorless. In order to have that, what that ends up being is that it obeys an SU3 symmetry. And then for the charged weak interactions, so anything that exchanges W plus or minus boson, you have weak isospin, and this obeys an SU2 symmetry. So basically, symmetry groups are mathematical descriptions of interactions between collections of objects. So basically, the way that you want to think about an interaction is like you have, an electron in some state, it goes into an electron in another state. The way that that transition happens is through some sort of mathematical. If you're going to do it if you're going to model it in the standard model to make a prediction, it's an exchange. It has to follow these symmetry interactions. So here's a toy example. I know it's kind of, hopefully you guys are with me. I can't see your faces in the group, so I don't know, and in the room, so I don't know if I'm losing you. But here's a toy example that I really like. So these are 6 triangles, and they're all related in some way. So what I mean by that is one of these triangles can be transformed into every single other one of these triangles. So they're all related by a symmetry group of interactions. So I want to say this group has what symmetries? So it's A, rotational, B, mirror symmetries, C, both, or D, neither. And I imagine this to be I was hoping I'd be in person and you guys could just yell it out and I can hear you. I realize that's probably not going to happen, but I want you to say, what do you guys think? How do you guys think that these relate to one another? Maybe. All right. Great. I'm getting some answers in the group, and both C is what I'm seeing in the chat. Hopefully that's happening in the room. And the answer is yeah, both. So together, these symmetries describe all of the relationships between these triangles. It is indeed both. This is the role of the U1, SU2, and SU3 symmetries of the standard model. So basically, 120-degree rotations map all of the triangles across the rows. So if you rotate them, that's how you get this from this triangle to this triangle. And then mirroring through the center is how they relate across the columns. These are the interactions or the forces that relate these triangles to one another. And the U1, SU2, and SU3 of the standard model do this for all of the particles that we have. Excuse me one moment. The interactions were really paramount for us to be able to have the predictive power of the standard model. So here I have, a brief snapshot in time when we were really discovering, different bound states of particles, kind of hand over fist. Just as soon as you would put something in a beamline, new particles would fly out. This is what we consider kind of like the cowboy era of particle physics, where anything would give you new particles if you put it in a beamline. And we end up having all these new particles, and people were really in a rush to understand how they related to one another. But when you discover them, you can measure things about them. You could measure their mass, their charge, and their spin. And because of these things, you're actually able to map relationships between them. Because of this, because of the relationship between all of these different particles, which was called the eightfold path kind of at the time, we were able to deduce kind of that they must be related to one another through an SU3 symmetry. So in order for all these particles to make sense together, scientists were able to understand that, well, there must be something more fundamental to all of them. And that was how they got the quark model of matter, and that those quarks must interact through this SU3 symmetry. Basically, when you impose that sort of mathematical relationship on 3 quarks, you were able to kind of get this diagram out that proposed the new particles. And this was really where we started to understand the symmetry nature of the standard model. So there's another way that symmetries interact. This is another kind of toy example. So I said earlier that, of course, A to B, if you move it in space, that's momentum conservation. But you also can have another type of coordinate transformation. Like here you have, say you wanted to rotate the my coordinate plane here. There's no reason to think that rotating these axes should change the physics at all. This is spatial symmetry. This is what would give you conservation of angular momentum in a normal thing. But rotating it shouldn't change the physics. This is, this is, of course, the same for the symmetry groups of the standard model themselves. Small rotations within each one of these groups shouldn't change the fundamental physics, and this ends up being true. And excuse me. Now, of course, since this is operating on particles and we're in a quantized world, these shifts also have to operate in quantized systems. And we know that the symmetry themselves are perfectly observed or perfectly conserved because we've actually measured them, and we know that these symmetries are demanded. And the only way that you have the symmetry preserved is the addition of a boson through these small rotations. And that boson is then how we get, or the addition of those, excuse me, sorry, I think I've gotten a little off track. The symmetry is only preserved with the addition of a boson. So since we knew we had the symmetry, if you want to have a small rotation in it, That also shouldn't change the physics. From that, you actually mathematically get out the need to have these the gluon, the photon, and the W and the Z. And we know that the symmetries are respected because we've actually measured them in particles. So bosons come naturally from these symmetry group interactions. We have two different types for the most part. We have massless, as math intended them to be, because perfect symmetries, which we've seen happens, means that these bosons have no mass. That's the gluon and the photon. And then we have massive bosons, of course, and this is as nature intended them to be. We know that they have mass because we can measure it. And then the question is, okay, so what broke these symmetries that allowed it to have mass? And then that was ultimately the question that we had in the standard model. And it turns out that the Higgs is what allows the W and the Z bosons to have mass. The Higgs boson broke some larger perfect symmetry group into the U1 and the SU2 that we actually see in the standard model today. And that's why the W and the Z bosons end up having mass. And of course, this also allowed us to have interactions that give us masses to all of the other charged fermions. Before that, we just had to put the masses in directly. We knew that they all had mass from experiment, but we didn't have a theoretical underpinning of that. Once we discovered the Higgs boson, or the Higgs boson was postulated, that gave us a mechanism that related all the particles together that allowed us to have mass in the standard model in a way that wasn't just ad hoc and added in. All right, so let's stop for questions again here. So feel free to, I'll bring up the chat. Maybe if I can bring it back up. And are there questions in the room?
Yeah, we already got a couple.
Great. Maybe we should start with some in the room.
Can you explain more what the Higgs boson does? Like, how does it break the symmetry? Like, what does it do, I guess?
Oh, that's a really hard question. How does it break the symmetry? I would almost say that that's one of the and please, other scientists in the room, save me if I say this wrong. But it's almost more of the way that the Higgs potential.
We've got I guess a chance from Jeanette. Go ahead.
Yeah.
I the Higgs would say that you can think of it like it offset from 0 in its middle. And the fact that you have that offset results in, that is how you can think of mass. Anything else around, you know, head. I think it really is a mathematical question. Field and its offset, which is non-zero, a constant number.
All right, it looks like we got one other in the room. I don't see any on chat. How are we doing on chat?
We have one on chat, which I guess I can answer while we're walking to the person in the room. And it's, since we know these symmetry groups, why can't we find mathematical connection to unify these forces? That's a good question. I mean, we've shown with the Higgs boson, we've managed to unify the electromagnetic and the weak, but then that leads the question, why can't we also unify, UCD in with this? And the answer is you sort of can mathematically, actually. There are plenty of larger order symmetry groups that people can postulate that would unify all these forces together. But with those larger symmetry groups, that implies generally the addition of more particles. And there's a couple of reasons that this then becomes complicated. If you have additional particles, if they exist at energies accessible to the LHC, we should be able to measure them. We should be able to discover them and see them, and we don't. So okay, that's then anything that answer, that goes that way is kind of ruled out. So that doesn't mean that there aren't still larger symmetry groups at higher energies that aren't accessible by the LHC, but then we can't measure them. So the answer is, I think everyone really believes that they are connected, and mathematically we can write formulas that do this, but we can't experimentally verify them. So well, let's maybe go back to one in the room, and then I see a few more on the chat that I can then field.
Why does the Higgs boson give mass to the W and Z bosons, but not to the gluon and the proton?
So that just comes down to the function of the W and the Z. So the W and the Z boson exist because the Higgs breaks the larger electroweak symmetry. The SU3 of of QCD, that's separate and perfect, and that's why the gluon is there. So that one doesn't need mass, whereas the Higgs is kind of what does it for the W and the Z. And then of course, now the photon is also in that group, but it just sort of shakes out that way when it's broken, that the U1 is perfect. That's probably not a very satisfying answer, but at least that's how I think about it. That just is kind of how nature worked out. And I see one here that since we know the Higgs boson has never been seen or measured, how do we know it exists? That's not true. We have measured the Higgs boson. We discovered it in 2012 at the LHC. We measured it. Janet works on it and has a couple of really great new results out. So we have seen it. And she can talk in the next talk about how we actually measure it at the LHC. So that's all the Zoom questions. Are there any other ones in the room about this? And then we can move on.
We had one more Zoom question earlier, and the question was, how do you measure the spin of a particle?
That's a really good question. You can do it with magnetic fields. So spins mainly manifest. You can tell them separately through magnetic fields. So you can, when you have particles come in, you can apply a field, and then based on the spin, it'll either go up or down, basically, as it travels through this field. So that's how you can do it, how you can separate them out. Oh, and we had one more in the Zoom, which is how can fermion...
There's also one more in the room as well.
Oh, let's do the room one then.
Well, these should probably be the last two, but.
Does the Higgs only interact with standard particles?
That's a really good question, and one that we actively study at the LHC. So like I do an analysis right now that would have the Higgs interacting with non-standard model particles. That's Janet does a lot of that, so she's a world expert on that as well, and studying that. So the answer is we don't know, and we're studying it actively. Okay, so I said I would answer one more from Zoom, and the question was, how can fermions have half spin, and does this have anything to do with the extra dimensions? And the answer is no. The spin is just a property of the particle itself, and it doesn't have anything to do with extra dimensions, but extra dimensions can deal with some of the other questions that we had of, can all these forces be unified and that sort of thing, but it doesn't relate to spin. Okay, so I'll continue with my talk. And so I'm closing the chat so I won't see it, and then we'll have time for questions one more time at the end with me, and then we can move on to Janet. All right. So earlier in the talk, I flashed this diagram of the standard model. So I showed you this one first, then I showed you kind of the structured one where it had all of them grouped by how they interact with one another. But I like this one for a few reasons. So here again, it has all of the particles of the standard model. And I like this one because it's symmetric and it looks complete. Everything fits together nicely in this diagram. And it kind of gives you this false sense that the standard model, is complete and is fully described. But this just, isn't true. Earlier, I told you that it only covers 3 of the 4 fundamental forces, and all these things have mass. And then the obvious question is, doesn't mass interact with gravity? And the standard model, as it is, does not comment at all on gravity. And that's a pretty big oversight, at least in my opinion. But that's not the only shortcoming of the standard model. Of course, it doesn't talk about gravity at all. We have the open question that neutrinos have mass. I haven't talked about that, but neutrinos shouldn't have mass in the standard model. We, of course, have the cosmological observation of dark matter. None of the things that I've talked about so far deal with dark matter. And then we have kind of more existential questions about the standard model, like things like the hierarchy problem, which are basically like, why does the Higgs have the mass it does? There isn't really a good reason for that in the standard model as it exists. So even though it describes the world that we live in and it allows us to make really good predictions about how particles of the world interact, it really doesn't completely compose all of the things that we know about the universe, which means it's just fundamentally incomplete. And we have had, several phases of exploration when it comes to standard model physics over the years. So I like to consider, this kind of early 1900s, the Wild West of particle physics. We had questions, but basically all discoveries were surprising. We had the electron, we had the atomic nucleus, we had the proton discovered. Here, experiment was really outpacing theory. Things were coming out and we didn't know what they are, and that was really exciting. This was really when, the quantum nature of the universe was being understood. Then we entered more of a roadmap kind of period of particle physics. Theory in this place outpaced confirmation by experiment. We had this legacy of where a particle would be proposed and then later experiment would find it. And people were able to design experiments specifically targeting different particles to make sure that we could then, build the pieces of the standard model one by one. And now we're actually kind of back in uncharted territory. And for me personally, this is really exciting. The standard model no longer is predicting new particles. It still is predicting things that we have not necessarily experimentally seen. I don't want to, make it seem like that the standard model is done. There's still lots of interesting physics to be done there. But we're really back in uncharted territory. We still have those open questions. What is the standard model's relationship to gravity? What is the standard model's relationship to dark matter? These are still open questions that we don't have good answers to, and we also don't really have a good idea of where to look. So we're really back into the Wild West regime again. So we're back where experiment needs to lead the way. And here I have my favorite picture of the CMS experiment, which is the one that Janet and I work on that's based at CERN. And there's kind of two ways that experiment can do this in trying to understand more about the universe. We can measure the particles that we have very, very, very carefully. And this is important. And this is something that we really need to do. This is testing, like, are the standard model predictions really that good? I've kind of given you the broad strokes where, it postulated a particle and then we discovered it. But it also postulates things about the particle, how often should it interact, other relationships that it should have, to make sure that we really, really understand those and see if they really are behaving in the way that the standard model predicts them to do. That's one kind of class of experiments that we can do. And the other thing, of course, that we can do is we can look directly for new particles. And this is going into answering some of the other questions. Like one of the questions that we had is, how do we know that there aren't these larger symmetry groups? The answer is, we don't, but we can look for signatures of those. And that's what I do, for example, at the LHC. And then that kind of brings me to the end of the standard model talk. So we have time for questions again. Again, I want to point you to the quiz. I find this kind of fun. So we can answer some questions, and then I think Janet can take the stage, or there's a break. I'm not totally sure.
So we're going to take some questions, and then we're going to walk around.
Okay.
All right. Do we have any on the chat? How many we got?
We have a few. So the first one is there any particle that opposes gravity? Not so far.
Oh, wait. We got some in the room. Okay. So you take one. We'll switch off. One on chat, one in the room.
Okay, that sounds good. So yeah, so the first one was, is there any particle that opposes gravity? I would say not so far. I mean, I guess you could say that photons don't, but I think they even bend in space-time. So I would say, yeah, not so far. All right, so room question.
So for the symmetry groups, so is that just basically all the transformations that you could impose on a certain particle, or is that is there a different way of looking at it?
No, that's exactly how you should think about it. I'm glad. I think I muddled through that part of the talk a little bit, so I'm glad that that's the conclusion that you got. Yeah, it's the symmetry groups determine the transformations from one state of a particle to another. That's kind of a physics quantum-y way of saying how one particle relates to another, and that's how the symmetry groups do govern that. And of course, the different particles will interact with different symmetry groups. It's how you can have like the top quark interacts with the strong interaction, and it can interact with the weak, and it can interact with the electromagnetic. Like all of those things happen. And then each one of those symmetry groups governs how it can do those things. Okay, I guess that leads to one on Zoom. And the question is, what do you think about how string theory model gravity compared to the standard model? So to me, string models, they're extensions of the standard model. Any string model that could possibly be real must also respect and give you standard model predictions because we know that they're true. The question then becomes, can we test string theory, string hypothesis predictions? And that's where it gets harder. String theory makes concrete predictions about the number of dimensions of the universe. Well, that's not really something that we can detect at the LHC, which is what makes it harder. So they're not incompatible, but any larger string model that would incorporate gravity must also give you the standard model in lower energies. So I guess now back to the room.
What is a pion? Why wasn't it in the standard model? Because on like the list discovered particle there, but it wasn't in the standard model.
Yeah, so pions are bound states of quarks. So you can put quarks together and make pions. That's ultimately it. So it was one of the ones that allowed us to infer the quark nature of the standard model. Because before we got the pion and we thought that that was the fundamental particle, but it's not. It's actually made of quarks. All right, so then we have okay, so we have, does the standard model indicate the possibility of extra dimensions? I would say no, it doesn't, but extra dimension type models are ways that you can extend the standard model to answer some of the other questions of the universe, is kind of the way I would put it that way. So yeah, maybe one in the room.
Doesn't look like we have anyone in the room.
No more in the room?
Your chest.
Okay, so then we have a...
I got it all? Looks like they understood what was going on in the room pretty good. So.
Great. Then I'll maybe field a few more on Zoom. Aren't that many, and they should be pretty quick. Okay. So one of them is gravity, the only fundamental force that interacts with all the fermions. No, the weak force also does. And then I don't actually know the answer to this one, where it's, does string theory or loop quantum gravity give a better description of gravity? I would say I don't know, and I don't know is the answer there. General relativity gives the best description of gravity. Would be my answer there. And then the question here is, what is the muon, and is there any reason why its existence wasn't predicted before its discovery? So muon, you can think of it in its most basic way as just a heavier version of an electron. And back then, we didn't actually know that there were different generations. So the way that we think of the different columns of the standard model that I was showing you earlier, we think of them as generations of particles. So like, everyday matter is kind of in this first generation. Then you have a second slightly heavier version, and that's where you have the muon in, that would be kind of the stand-in for the electron. There wasn't really a good motivation to have that, which is why we didn't see the muon, or why we didn't predict the muon in the beginning. And now that we understand that there are these other generations, well, then the muons exist and makes perfect sense. And then finally, should there be the same number of bosons as symmetries and as dimensions we have? So the bosons are related to the symmetries of the interaction. You can count them in a way, but they're not directly related to the number of symmetries. It's more related to, but they're kind of related to the number of symmetries. But like, for example, with the W, you have the plus and the minus because it's related to the charge current. So you need to have like a boson for every type of interaction. So you have a neutral one, which is the Z, and the photon, and then you have the two charge plus and minus in order to allow that to happen. So it's loosely related. There's probably a better mathematical way, but I can't pull that out right now on Saturday morning. I have to think about it. And then, can bosons feel gravity? This will probably be the last one I think I should field. Naively, I would say yes, because they have mass, but there isn't an experiment testing it. So yeah, that would be my answer there. Maybe people in the room have other answers to that. But yeah, I would say probably.
I can say a couple words. I mean, we know that photons feel gravity. I think that's been the one that's been experimentally tested through eclipses. I think there's some priors that gluons would feel gravity because we know that protons have mass, and we have tested the equivalence principle that everything inside on a neutron the same way because protons and neutrons have the same inertial and gravitational mass, and presumably have different ratios of quarks to gluons. So I think there's some assumptions that they would, but I think as you point out, we don't know empirically that W and Z bosons feel gravity, but we have every reason to think that they do.
Yeah. This is a fun question. And then I think we should probably move on. But can gluons exist as independent particles? No. and this is really important to LHC physics. Actually, quarks themselves, anything that interacts with QCD has to interact. Okay, there's some caveats. Has to be be colorless to be stable. So a single colored particle like a gluon or a quark can't interact on its own. It has to then form this bound state. So that's a good question, and really, really fundamental. So the answer no, and that's an exciting reason why. All right, I think I can be done. I'll stay connected, so if people have questions, I can help answer. But then I think we can take a walk.
Everybody, let's give Grace a hand. So we are back from our break. We're going to get started on the second portion. Janet, whenever you're ready.
Hello. Let me move this closer to my face. That's acceptable? Good. So hi, I'm Janet. I am a postdoc. Do I need to like? Okay. There. I'm not the loudest person ever. So. Yeah, I'm a postdoc here at Fermilab. That means that I finished my PhD and now I am a few years a job. I did not know what a postdoc was, so I always like to explain my job. I've been here since 2020 and I work on the CMS experiment. So I'm going to talk a bit about we do physics with the Large Hadron Collider. So what I'll start with is why would we build a high energy particle collider? Okay. Okay. Right, so I'm gonna like, as far as I can to the side. So the answer to why would we build a high energy particle collider is that we want to study the smallest things. So in quantum mechanics, there's this relationship between particles and waves. And basically the energy of a particle is inversely proportional to its wavelength. So I have this in here where lambda equals e, where c is the speed of light and h is the Planck constant. So it's in units of intrinsic angular momentum. And basically what this is telling us is if we look at things with very big E, we're actually looking at things with really small lambda. So you can see here this kind of diagram of an atom, where when we talk about the size of an atom, we're talking about something that's 10 to the minus 8 centimeters across. When we forget about the electron and we look just at the protons and neutrons at the center of the atom, we get down to about 10 to the minus 12 centimeters across. And then when we look at one of the protons or neutrons, it's again a factor of 10 smaller. And when we look at a quark, as far as we know, this has no radius at all. But really all that we can say is we know that if it has any sort of radius, it's less than 10 to the minus. This is what we're trying to do by increasing the energy of our particle colliders. Also ask, talking about high energy, but what is high energy actually? So we can talk about a proton, which is a little bit intuitive, a little bit not intuitive, and how much it actually weighs. So it weighs 10 to the minus 24 grams, which is 1 giga electron volt. So that's super small. These electron volt units are probably something you've seen if you've taken a physics class. It's the energy that an electron gains when it's accelerated over a potential difference of 1 volt. 1 GeV, giga electron volt, is 1,000,000 electron volts. So to accelerate an electron to 1 GeV would take a stack of AA batteries going all the way around the world from Geneva, Switzerland, not Geneva, to Chicago, the long way around the world. So that's really high energy. And then proton energies at the large collider are 30. So that's trillions of electron volts, which is high enough to probe these length scales of what we know to be the smallest scales that we've measured. So instead of me telling you what the Large Hadron Collider is, I will let Stephen Colbert tell you.
I spent a lot of time right over there, isolating the biggest, newsiest stories of the day and containing them in the most topical circular tunnel with a circumference of 26.7 kilometers and a depth ranging from 50 to 175 meters. Then I add 2 adjacent parallel beam lines which travel in opposite directions around the ring, intersecting at 4 points. I add 1,232 dipole magnets to keep the beams in their circular path, while an additional 392 quadrupole magnets are used to keep the beams focused. Then I add stronger quadrupole magnets close to the intersection points in order to maximize the chances of interaction between the 2 beams cross. Also, I can smash joke protons against each other at near the speed of light to generate the Higgs boson heavy comedy particles that make up my nightly monologue.
So that is Stephen Colbert comparing his job to mine. We basically do the same thing. But like you heard, the Large Hadron Collider is a circular proton-proton collider located at CERN. This is an international lab in Geneva, Switzerland. It actually spans the border of France and Switzerland, so they split the electric bill. And there's a lot of math involved, both to keep these charged particles moving in a circle and to keep the beams focused so that they don't spread out. So you can see here a picture from the LAC tunnel. It's all located underground. And these cylinders here are some of the dipole magnets. And then this is a very famous landmark from CERN called the Globe. So what actually happens in an LHC collision? We have these very large rings that we fill with bunches of protons. So it's not like protons go around one by one. We actually have very large bunches of protons with 100 billion protons in each bunch, and they cross 40 million times per second. So they cross super frequently, and there's a whole bunch of them crossing at the same time. And when the bunches cross, if we're lucky, we will have a parton, so a quark or a gluon from each proton interact with a parton from another proton in a way where they exchange a large amount of energy. And that is something that we consider an interesting collision. One thing that I also always like to point out is we talk about the center of mass energy of the proton-proton system at the LHC being 13 TeV. But there's a lot more in a proton than just a single quark or gluon. So there is no parton in proton that carries the entire energy. So most of the collisions that we look at are actually at a center of mass energy that is substantially lower than 13 TeV, even though the proton-proton system. So what happens in an LHC collision? Well, we've done this a whole bunch of times. We've done 10 to the 16 collisions so far. And by the end of 2040, we're going to do another factor of 20. And every collision starts the same way. So we have this 13 TeV proton-proton system. But there are actually a lot of possibilities for what comes out. So I like to use this quote that insanity is doing the same thing over and over again and expecting different results, which is talking about quantum mechanics, absolutely what's happening. So quantum mechanics is insane in this specific way. So we can use quantum field theory to predict what particles are going to come out. We can never say for sure, but we can say with some sort of probabilistic estimate that this is what we expect will happen this fraction of the time. And then here you can see this is sort of a cartoon of a Feynman diagram. What this is showing you is on one axis space and on the other axis time. So you have 2 protons in this example that are moving parallel to each other in space. They interact through 1 quark from that proton and 1 gluon from this proton at some time. Stuff comes out, and then you get a whole bunch of particles, and that's what we measure. So this is a diagram of the LHC. So this is all located 100 meters underground. This is the big ring. And there are 4 primary experiments that are located on the ring at the places intersect. So one is called ALICE, which doesn't study proton-proton collisions. It actually studies something completely different that we do for a small fraction of the year. So actually right now, this usually happens in the fall, collisions of heavy ions in the LHC. So we're not actually running protons around the LHC ring right now. We're running heavy ions. And ALICE is an experiment that is built specifically to look at these collisions, although ATLAS and CMS look at them as well. We also have this experiment called LHCb, where the B is short for a bottom quark, or beauty quark, depending on who you ask. And this studies particles that contain these bottom quarks and other heavy quarks like charm quarks. And then there are two experiments that are sort of sisters on either side of the ring that we call general purpose experiments. So here at Fermilab, we work on the CMS experiment, which, as you can see, is much further from the city of Geneva than the ATLAS experiment and pain to get to, whereas ATLAS is right on the train. So if you ever visit Geneva, you can just ATLAS, easy peasy. So what is a general purpose experiment? This is something that I really like about CMS. It means that we study everything that we can. So there's no one measurement that we're interested in making. We have kind of a long list of measurements that we would like to make based on what we know already. So we know what exists and we want to measure them very precisely. But we can also look for stuff that we've never seen before. And we can also, sit around and think about new stuff and go back and look at our data and opportunity to look for stuff that we hadn't thought about before. Really cool. So the only requirements here are that we detect as many particles as possible, identify them correctly, and then measure their energy and momentum and other very precisely. Once this data set, we can walk away, we can think of new stuff we might want to, and we can revisit this data, and we have everything that we need already saved to do that. So what particles can we detect? Well, I like to group them in terms of their lifetime. So we have particles that have very short lifetime, where they'll decay or group together immediately into other particles, and they'll never actually reach the detector. So this here is an example of such a particle. You can see the original particle is this black line. Before it even reaches the detector, which is represented by this circle, you can see that it decays into two other particles. And what we actually see in our circular detector here is the two blue particles, not the black one. Yeah. We also have medium lifetime particles where you can have something that travels partway through your detector and then decays. So that's what this is representing here. You can see in the innermost layer of your detector, you would see the black thing. Everywhere else, that you would see the and then we also have stable particles that go through the entire detector. So you're seeing the signature of a single particle in every piece of your detector. So in terms of short lifetime particles, some of the most interesting ones are short lifetime particles. So the top quark, the Higgs boson, the W and Z bosons. I would say this is a reason that we haven't studied the effects of gravity on the W and Z bosons because alive. They live for 26 seconds. So not exactly easy to do. And then something else that I group in with the short lifetime particles are quarks and gluons. Do that not because they decay, but because they don't like to be alone, and they will immediately group together with other quarks and gluons and create these things called hadronic jets. These are super complicated objects that are basically a result of what Grace was saying, that you can't have a gluon, a quark alone. So an analogy that I like to use is you can think about if you have an atom, you can take the electron off and you can have an ion. Strong force, you can't have an ion. Be neutral under the strong force. So a single quark has some charge under the strong force. That's a no-go. You need to get another quark in there in order to. So this is a very active area of study. And basically what we end up with every time we have a quark or a gluon is this spray of particles that turn into eventually hadrons, which are made up of states of quarks and gluons. So I count those as having a short lifetime as well. We also have a bunch of particles with this medium lifetime, like the tau lepton, which is the heaviest. Also hadrons that contain charm or bottom quarks. So when you have quarks that group together and one of those quarks is a bottom quark, or one of them is a charm quark, those tend to live a little bit longer than something like a pion. And then we can have stable particles. So these are things with lifetimes that are long enough that they move through our whole detector. So here you have the muon, the electron, the proton, and the neutron. Arrows here to indicate that we actually don't know what the lifetime is, but it's definitely longer than this. Okay, so from the point of view of the detector, the stuff that you see in the detector is hadrons, photons, electrons, and muons. So that's a pretty short list, right? Everything else either decays partway through the detector or decays before it even reaches the detector. So that's a very short list, but we can use these as building blocks to reconstruct any type of particle. So we do this by grouping the different building block particles together and analyzing the relationship between them. Example, which is studying dark matter. It was not on my list of things that we can actually detect at the LHC. And I'm not going to talk a lot about dark matter. I think somebody else probably will. A lot of dark matter experiments that you hear about are basically like big tubs of stuff where you sit and you wait for dark matter to come, and you do it long enough that even though it happens rarely, you see it sometimes. That's how you usually detect dark matter. You can also do it at the LHC by saying, maybe I can produce it by colliding protons. If you collide enough protons, maybe you'll actually notice. So depending on its properties, this is something we might be able to do at the LHC. But if this is an interaction that you have, what do you actually see in your detector? Nothing, right? Because it's very unlikely that this dark matter particle is actually going to interact in your detector, even if you produced it in your collision. So what we actually do is we look for these examples where one of the incoming protons radiates another type of particle. So if you have a quark, it has charge and it's charged under the strong force, so it can radiate a boson associated with those forces. So you could get a gluon coming off, or you could get a photon coming off. And then what you can do is you can say, I know the momentum. I know the momentum of my incoming proton-proton system, and I can measure the momentum of my radiated particle, and then I can infer the momentum of the other stuff that was produced. So here we use conservation of momentum to notice that there was actually something that we can't see at all. So here is a picture of this actually being done. I think this is in the Atlas experiment. This is a signature of a potential dark matter event. It doesn't happen enough times that we can say, haha, we saw dark matter this way. It does happen occasionally. You can see that there is a large hadronic jet in the detector over here. That's what this is. And then this big red arrow is representing the momentum imbalance. So this is the type of event that we can look for at the LHC that has only the building blocks that we know about, but we can use it to make a statement about some other type. So I think this is a good time to stop for questions.
The LHC can't put me know the low G drink books.
So
That's not on the list, right?
You can tell that they were there because they will form one of these jets. What we actually measure at the Large Hadron Collider are these jets.
Measure them similar. Assume that they're based on.
So the jets will definitely leave signatures in our detector. So this is an example here. So we have a bunch of different layers of our detector, and the jets will be just a spray of particles. All of those particles will, charge energy in some. So we don't have to infer that they were there. Momentum imbalance. We can actually see the detector. Aha, here's a picture of a lot of particles going through. This is.
Are there other situations in which you have a momentum imbalance? And if so, like, how do you see that and tell what it might be?
So another example, can anybody think of a particle that I did not mention? If you haven't been hearing, right? So neutrinos are very unlikely to all these other particles that we're talking about. And so there are examples when we have, for example, the decay of a W boson. A W boson can decay to an electron and a neutrino. Then what we can do is we can look at our electron, we can look at our missing momentum, and we can reconstruct the mass of that. Take the mass of a W boson, then we can say, aha, there was a neutrino there from the decay of a W. So there are a lot of examples where we use this missing momentum.
How do the detectors work? Like, how do they detect different?
So that is the whole next section of my talk.
Okay.
Question on Zoom is, you can try to detect dark matter by colliding protons, but how do you know when you create it?
So you don't know whether you've created dark matter. You can say, I saw 100 instances where there was missing momentum of this. You can say, I expect that sometimes in the standard. Do I expect it 100 times? Yes. Okay, I didn't see anything extra, therefore there's no dark matter produced this. Or you could say, I expected that 10 times in the standard model. What's going on? I definitely see something. In terms of saying that it's dark matter, you need to do a lot of extra work in order to verify what it is.
Related to that, in the sense, are the properties of dark matter actually being measured?
So one of the properties that you have to have in dark matter to see it at the Large Hadron Collider is that it has to interact in some way with standard. I think that's true. Any hope of detecting dark matter and indirectly through gravity signatures is that it has to. Beyond that,
So you said dark matter can be like created. What are the like specific conditions for it to be created?
well, so generally you have to have some avenue for the dark matter particle to interact with the stuff that's in it. So we know that it doesn't interact with light. Interact with some other particle that's produced by quarks or gluons. It needs to be of a mass at our 13 TeV collider. We can't produce a 14 TeV particle with a 13 TeV collider because concentration. But yeah, I'm not aware of any other.
Right, folks.
I'm going to keep going. So the next part of this talk is, now that we have these basic particle building blocks, we actually measure them. We need to be able to identify them, and we need to be able to measure their properties with our detector. So the answer to that is extremely complicated, and this is a picture of it. So this is the CMS experiment, and I think later we're going to have a video tour we actually reported earlier this year of the CMS experiment. Right now, everything in the CMS experiment is closed up because we are colliding heavy ions there, and unfortunately no live tour, but excited for getting data. So this is the partner experiment of CMS. This is the ATLAS experiment, the one that I said was closer to the city and on the train route. The big difference between ATLAS and CMS is ATLAS is much larger and has a very different magnetic configuration. So CMS has a magnet here. ATLAS has a magnet here. And then also all of these things with orange tape are magnets. Toroidal magnetic. But both of these detectors are constructed in roughly the same way. So they have, I would say, 3 layers, where the inside, close to the proton-proton collision point, we have what we call trackers. So in this diagram, the protons are coming in through this orange pipe, one side, and then in from the other side, and the collision is happening. This blue stuff is representing the trackers, and stuff in the middle that we call calorifiers. And then we have some stuff on the outside that's actually not this red, it's actually the gray interleaved with the red that measures our muons. So I'll go through each of these layers in a little bit of detail. The inside part is trackers, and the point of this is that we want to measure the trajectory of a particle using pixels. So pixels like you have in a camera. A diagram here, if you have a charged particle moving through 3 planes of pixels, okay, aha, I saw something here, I saw something here, I saw something here, and then I can reconstruct a particle sort of connecting this connection of the dots is called a track. One thing that we really don't want in our tracking detectors is for this material to be very dense. This material, our particles are going to be deflected, and we're not going to measure the track as it would have happened in empty space. We're going to measure it with a lot of complication added because it's of our detector. For this material to be something very lightweight, and typically what we use are silicon sensors. You can see a picture of CMS, layers of silicon sensors. You can see, like a computer chip. There's tons of silicon everywhere. This is very common in industry for building these detectors, but they only register hits from charged particles. So if a neutron goes through the silicon detector, we won't see that. I mentioned that there's these magnets inside of the ATLAS and CMS experiments. This is giving us a magnetic field inside the volume of the tracker, which make these tracks curve. So if you've seen your Physics 1 class, this is probably an equation that you've solved, the relationship between a magnetic field and the radius of curvature related to the momentum. So you can see that in this picture here. If your magnetic field is pointing to the board, it's making things curve in a plane that's parallel or transverse to proton beam. The proton beam is coming into the center here and out of the center. They're colliding, and then you have this magnetic field that's making your tracks. When you have very low momentum, you end up with stuff that's very curved. So that's all this yellow stuff over here. And when you have something with high momentum, it's going to end up being almost straight. So that's these tracks with momentum, these red ones here. Okay, so then moving out a layer to the calorimeters, the goal here is very different. Trackers, we want to measure the tracks. We want to measure the curvature, which gives us the momentum. Here, we want to measure how much energy a particle has by making it stop moving. So here we actually want really dense material, which we did not want in the tracker. We like to combine that with something that absorbs the energy of particles. So this can be single material. Here you can see this is a lead tungstate crystal. So this is both very dense and absorbs light. This is some calorimeter. Or this can be two different materials, one that's very dense and one that absorbs the energy that's deposited. You can see this kind of like accordion shape thing. This is what the ATLAS electromagnetic calorimeter looks like. And you can see, for example, an electron is going to come in, it's going to start hitting all this dense stuff, and it's going to start powering off other electrons, positrons, photons. Those are all going to be collected, and energy that's absorbed is going to give you a measurement of the energy of the initial electron. Okay, so then all the way on the outside, we have this huge system dedicated specifically to muons, because muons have a long enough lifetime that they move the entire way through CMS or the ATLAS detector. So you can see here like a little diagram where you have the detector is about its size, and then the muon system is just huge. The muon is a charged particle, so it does leave a track in the inner tracker section, and you can actually combine information about which of these different segments the muon went through on its way out with information from the tracker. So you can combine these two signatures and get really good measurements of muons, especially on CMS because they have their magnetic field. ATLAS built this huge new small wheel fairly recently. It's part of the detector now, but just to give you a sense of the size of it, this is some of the people that worked on it, and this is the part that goes kind of on the cylindrical detector, and the protons go through there. Okay, so then here we have kind of a pizza slice of the CMS detector. So the protons come in here, and then you see you get these layers tracker. And this is showing you how different particles are going to interact. So let's see, let's start with this muon, which is in blue. So this moves through the tracker. This leaves little X's in the tracker. It doesn't do a whole lot in the calorimeter. It doesn't do a whole lot in the magnet. And then it leaves these signatures in the outer system, which is muon chamber. And we have the electron, which again curves in the magnetic field, leaves some sort of signature in the tracker, and then is stopped in this inner calorimeter called the electromagnetic calorimeter. About a charged hadron, here you have one of those, so it leaves signatures in the tracker, and it has a bigger shower than an electron, so it needs this larger calorimeter, which we call the hadron calorimeter, to fully contain all of this energy that it deposits. Neutral hadron is almost the same, except that it passes through the tracker and doesn't see anything. And then photon, which also passes through the tracker and doesn't see anything. In the calorimeter, very similar. That's basically how we see all of these different things. One additional system that we consider part of the detector, but that I didn't really talk about, is that we make way too much data to save it all. So all of these detector systems have to make decisions very quickly about whether what they're seeing is interesting. I mentioned that we have collisions of proton bunches in the LHC every 25 nanoseconds. That's extremely frequent. If we were to save all of that data in 2018, this is what we would have ended up with from Atlas and CMS. And you can compare that to Amazon Web Services, Netflix. It's just like, this is obscene. Too much data, we can't do that. So we have to make selection very quickly in our detector systems about what we think is interesting. That gets us down to this little circle here. In the next phase of the LHC, we're going to collect even data than we've before. But even after we do this hardware level selection, we're going to end up with a bigger circle than we. So yeah, we save about 1 in a million collisions, and this is all called the trigger system. Very quick selection that we have. Okay, so maybe we can take a pause for detector questions.
Like the diagram up for like the different particles passing through, yeah, that one. How come some of them were curved and then like the neutral and the photon weren't?
That's a good question. Solenoid magnet. Oops. So this is giving you a magnetic field. I think, yeah, so it says out, but I don't. So if I do my right hand rule, are you? So this is an electron. It's negatively this red one. So so you have a magnetic field inside this solenoid that's going to make the electron curve in this. Neutral particles are not going to care. And then the muon, you can see that it curves one way and then it curves the other way. This is something that's unique to CMS, is this magnetic field is so strong that actually sort of the return of it gives us a magnetic field in the opposite direction, but weaker. So you can see this is 4 Tesla going in, and this is 2 Tesla. You do have a magnetic field on the outside of this solenoid that's going to make it curve the other direction. In Atlas, this is a much weaker magnetic field, and you don't have this outside, so you just have the muon curving, and then it actually, because of the toroid magnet system, will curve this way, and then it will go like this way, because it has a very different map in the two.
What causes a muon to go through all these different levels of a detector when most particles don't?
So a muon is what we call a minimum ionization. It means that it doesn't interact by ionizing very strongly. So it's not caught by, it moves only through the tracker. It's not caught by this because it's not interacting strongly with the material. I don't really have a better reason for why it doesn't interact in calorimeter, but long enough lifetime that it goes the whole. And even here in the outer part, we don't stop it.
Composition, the trackers and the calorimeters is so specific. Where do you get data from it? Where are the electronics? Are electronics?
That's a good question. There's stuff in here that's not what we call active. There's like holes and stuff that holds it in place. But mechanics. Stuff that keeps it cold. This all runs cold. And there's electronics. So there are like little boards and computer chips just throughout. So this is a challenge because all of those things are constantly getting blasted with particles, but that doesn't completely destroy them. When it comes to computer chips, and have something that's a computer chip that's programmed and it has a little area of memory, and then you can hit that with a high energy particle and flip a 0 to a 1 and everything is broken. Be very careful about the way that you design those electrons. They are in the midst of the tech. Particularly the cooling stuff, like if you have copper cooling fluid going through your detector, that's not good because that's a lot of material to deflect your tracks and your tracker. So you don't want that. So we have to be really careful to get low density material, radiation tolerant material, or all of this extra stuff that's not.
Do you determine what data to keep and what to like do you use or something to sift through that?
Sometimes. We're starting to do that a bit more. That whole system is called the trigger, and we have what we call a trigger menu. Basically, a list of things that we think would be super interesting. Energy photon, we think that would be interesting. Energy muon, because we think that will, with a list ahead of time. What we produce at the LHC is very interesting proton collisions. So like not a large energy exchange between two quarks or two gluons, low energy jets, and how to throw that away pretty much immediately. But we have to decide that in advance. We have to decide what we're going to save. Low in energy, we're going to try and save it if we're only going to keep the high energy stuff. That can be a hot debate, but what physics is interesting enough to save 100%. We also take some data that we call minimum bias, where we just save everything for a period of time. And the idea with that is if there's anything crazy happening at a high rate, we would look at the minimum bias and we would say, there's something here that we didn't think about. We need to adjust our trigger menu. Trigger menu also changes with time. So what it is now is not what it was in 2018. As people decide to focus on different things and harder algorithm things, so it's an evolving thing.
Quick question. So when you guys are doing the CMS experiment, do you guys change the strength of the magnetic fields as well to like induce different effects in the?
We don't. It's either on or off. Period of time that it was broken. We were taking data with no curved tracks. Makes things super hard, and that was really not a good time for us. But yeah, it's a fix.
Whenever you're ready.
The last piece of my talk, and I just want to walk you through a sketch of how to use what I've talked about to reconstruct a Higgs boson in an experiment like CMS. So the way that you produce a Higgs boson, LHC, has to start with quarks and gluons, right? It has to be something that's in the proton. But there are lots of ways that you can actually produce a Higgs boson. We call them production modes, and you can see the main ones here on the bottom. These are the Feynman diagrams. Gluon fusion is this little word cloud is showing you the relative contribution to the total rate of Higgs bosons from each of these different processes. And if I take my glasses off, like it's only gluon fusion. But these other ones are interesting because they're produced with different particles. So this is vector boson fusion, which is what I study now, where the Higgs is produced with two quarks. You also have a Higgs produced with a W or Z boson. Or this the first time that this was observed at the LHC, a Higgs produced in association with two top quarks. So what this is telling us about Higgs interactions depends on what the Higgs is interacting with in this Feynman diagram. Here you can see this is the straight line is representing a quark. So here we can see how is the Higgs interacting with quarks. Here we can see how is the Higgs interacting specifically. Very interesting question. And then in the vector boson fusion and the BH, you can see how is the Higgs interacting with your Z boson. So we can identify these different production modes by the extra stuff in addition to the Higgs boson. And they're interesting for different reasons because they're sensitive to the boson and the way that it interacts with different. Measuring the Higgs boson is more than seeing the Higgs boson, it's also understanding the entire picture of how it interacts with all the other stuff in the standard model. And the Higgs boson is my list of very short lifetime particles. So we don't see it directly. We have to look for what it decays into. And it can decay into a lot of stuff. Most of the time, it decays into 2 bottom quarks. A lot of the time, it decays into 2 W bosons. But you'll see, like on this list, it can decay into like a ton of different kinds of stuff that spans all of the different types of detectors that we just talked about. So there's no one part of the detector that's especially responsible for measuring Higgs. There's no one type of object that is used for measuring the Higgs. But actually, most of what we know about the Higgs comes from an extremely small fraction of the decays. So the Higgs decay to 2 Z bosons and the Higgs decay to 2 photons. You can see this is like a super small slice of the pie. But we do a really good job of measuring the Higgs with these because we're super good at measuring these types of objects. So I'm going to use the example of a Higgs decay to 2 photons. You can see a Feynman diagram of it over here, where you have a Higgs boson, outgoing photons, one with energy E1, one with energy E2, and then they're separated by some angle. Louder, okay, sorry. Yeah, so they're separated by this angle. Calculate the invariant mass of this system. It depends on the energy of each of the photons, which we measure with our electromagnetic calorimeter, and it depends on the angle between them. So if the photons truly came from the decay of a Higgs, we expect to see the diphoton invariant mass close to the mass of the Higgs, which is 125 GeV. This is never perfect because our detector isn't perfect. We don't do a perfect job on the angle, and we don't do a perfect job on the energy. CMS does a really good job on the energy, though. Okay, so here you have one of the most famous plots from, this is the Atlas discovery of the Higgs boson. So all that we've done here is counted the collisions that have 2 photons. And when you calculate the invariant mass, there's a lot of stuff that makes 2 photons that's not a Higgs boson. So when you calculate the invariant mass, most of what you get is not Higgs. And that gives you this continuously falling spectrum in this diphoton invariant mass. Basically, this mass is kind of like an energy. It's really easy to make stuff with low energy, so you have a high number of things happening here in the standard model. It's harder to make stuff with high energy, so this goes down as you go up in the mass. But you can see that in addition to this smoothly falling spectrum, there's this little bump here at the Higgs mass of 125 GeV. And if you subtract off the background, which they've done with this statistical fit, you can see, oh, hey, look, there's something there at 125 GeV in addition to this smoothly falling background. So this is a really famous figure from the Higgs discovery paper. And I hope that you understand how we got to this. So you might ask, what is next for the LHC community? We're not over with the Higgs discovery by any means. We are working towards the high luminosity LHC, which we call the HL-LHC, which is this upgrade to the accelerator that's going to allow us to get more data, so 20 times what we have before, and more than 100 times what we had when we discovered the Higgs. So a huge amount more data, which lets us look for rarer and rarer processes. We're also improving these detectors, partly so that they're not totally wrecked when we run the accelerator with this high luminosity, and partly so that we have some additional performance, so better tracking, things like that. And we're also already talking about the next collider that we want to build. But like the LHC, this is going to be an international effort. These things are expensive, and the building these different types of things is really all over the world. So you really do have to bring people together to do this. Questions that you can ask: is it going to be a circular collider like the LHC? Is it going to be a linear collider where you start with something here, and they just go in a line? A lot fewer magnets that way, and magnets are hard. What are we going to collide? Are we going to collide protons or electrons or muons? Something that lately that's been gaining traction. And then where are we going to build it? That's more of a political question, but that is a question. So we had last summer this meeting in Seattle, mass, where you can see all of these different people This is a meeting of the U.S. scientific community to decide what types of experiments, especially large-scale experiments, we're interested in prioritizing over the next decade or so. And eventually what we want to do is present that to the government and say, hey guys, we want to build these things for these reasons. Can you please give us that? So that's where we are. We're waiting for a big report from the government people in the next couple of months to give us some ideas what they're. Okay, so yeah, there's a lot coming still.